Recording there, and there we go. Okay, everyone, welcome to day 8 of Handmade Hero. We are on holiday time today. Wednesday, Thursday, Friday is going to be at 11 a.m. due to the Thanksgiving holiday here. And I would like to give a warm welcome to all the folks in Europe who are joining us today for the first time, because we are finally at a time where they can easily tune in. I think someone said it was about 8 p.m. in Germany right now. Not sure if that's right, but sounds good. So thank you everyone for joining us. This, of course, is Handmade Hero. We are making a game from scratch, and right now we are working our way through the Windows platform layer. If you would like to follow at home and you have pre-ordered the source code here, you will want to go into the zip file that you can download from the link that you got in your email. You can go ahead and unpack 007 from inside that zip, and that is the source code that we are starting with today. So if you want to follow along at home, that is what you're doing. Okay, I am going to go ahead and jump right back to where we left off yesterday. I have one thing that I'll maybe talk about at the end of the stream that came in an email, again dealing with direct input, but I'm going to save that till the Q&A for now. I'm just going to jump right in here. So I'm going to launch our trusty Emacs. A lot of people have been amusingly getting into Emacs. I think I specifically said it's too old of an editor to start learning now. Try to find something else, but people have been jumping on it anyway, and that's pretty hilarious. Emacs, the editor that won't die, people. Anyway, I'm going to open up Emacs here, and we're going to take a look at where we left off. Basically, what we did yesterday is we wrote this init DSound function, and you can take a look at it here. It's very simple. Basically, what we do is we load DirectSound directly. We get a pointer to a single function, and that single function is a function that we call to basically give us back an object. So this is basically C++ linkage. It's COM, which is Windows' sort of implementation of C++ across the DLL boundary. But basically what happens is we are just calling a function, and it is giving us back an object that we can use to call further functions on. That literally does mean that we are essentially getting back an object with a vtable. Now, we are not really going to be covering C++ very explicitly on this stream, but I will simply mention what this is for those of you who are wondering how this all works with this little arrow here. I think it's worth explaining now that we've kind of got the code working from yesterday. It's worth explaining how this works. So normally, if I have something like this, where I type in a struct like that, basically we saw in the intro to C stream and in this stream as well, we saw that basically what that does is that tells the compiler to lay out a particular piece of memory so that the things that are in the struct basically come together, possibly with some padding in between them, but basically in the order in which they occur and in the sizes that they occur. So if I do something like this, I will end up with a 32-bit X value and a 16-bit Y value anytime I ask for one of these. So if later I declare one of them, I basically get the X and the Y value. Now that is what is in memory. But C++ allows you to do some extra things. You can do something called a virtual function declaration, which we will not be using in the stream, but you can do it. Basically what it is you declare some function, just like any other function you might declare. But basically what happens is, instead of actually just hard coding calls to that function, so if later we were somewhere and we had one of these foo objects, right, we would call it as if it was a method. We'd put the dot on there, and we'd actually call it like this. It's just like any other function call at first. It looks the same, right? You can pass parameters to it, this sort of thing. That's exactly what happens. But there is a catch. If you were to just do this, there'd be no difference really between it and a normal function. It'd be exactly the same. The only difference is actually syntactic. So basically, if I actually, this is how I'm going to speed through this because we're not going to be using them. I just want you to kind of understand what's going on. So this is how you would declare it. Basically, it's the exact same function declaration that you've seen everywhere else, or I should say function definition you've seen everywhere else, but you put this foo : prefix on it, which basically is what's called a scoping. It's called scoping in C++, or the scoping operator. Basically what it says is this bar is not actually just a function at file scope. It's actually a function that's declared inside this foo object. And so you can't just call it. You can't call the function like this. You got to call it off of one of those foos. And what actually happens is, in this, the compiler implicitly actually rewrites the way the function is under the hood. You won't see it do this, but it'll do it. It'll basically insert a synthetic parameter here called the this pointer. And the this pointer will be basically used as an implicit way to reference anything that happens in the function. So inside this function, if I were to reference C, I can just reference C. If I were to declare a new variable, I can declare a new variable. It works just like any other function. But if I were to reference X, say for example, C plus equals X, normally X would be undefined here. There would be no way of the compiler resolving what X meant. It would say that it was undefined, and it would ask you to define it. But in our case, that is not true, because that this pointer that gets implicitly passed here, this thing, basically it will check to see first whether it could have referenced something inside that this pointer. And in this case, there is an X there. So this gets turned by the compiler into that automatically for you. That is the only real difference in these functions. Basically, it allows you to sort of have this free sort of lookup that you wouldn't otherwise have. And there are some other things that I'm not going to go into. They're totally against syntactic and basically features that about C++ that we won't be using. But the thing that I wanted to talk about more explicitly and that bears understanding, or is worth understanding in order to understand what's happening with DirectSound here and COM interfaces in general in Windows. Again, COM is C-O-M. It stands for Component Object Model, if you would like to look that up. Again, we won't really be covering it in detail here because it's not really relevant to us, but it is what we are calling through at the moment. Basically what happens here is I can declare this function virtual. And what that means is that it's actually more complicated than a regular function. It is not just a syntactic thing where it's inserting a little fake parameter for us. There's more than that. What this will cause the compiler to do, this virtual function, is it will cause it to insert, basically up here, it will insert what's called a vtable pointer. And basically what a vtable pointer is outside here, there will basically be, the compiler will declare this globally, it will declare a vtable for foo. A vtable is basically something that contains a bunch of function pointers. It's basically got pointers to the functions that should be called when you are using a foo. And basically what happens from now on is when you do this foo bar, instead of just putting out the code for an actual function call, what it does is it looks up in this table. So first it'll do look up bar in the vtable for foo using the pointer. So using foo's vtable, actually literally going and looking into the table. So it gets the pointer out of the top of foo, the one that the compiler silently inserted without telling you about it. It just silently inserted that pointer. It'll go look at foo vtable. It'll look at the index in the vtable to which bar corresponds, and it will then jump to that address. So if you remember, we basically did this sort of stuff up here ourselves. We declared our own function pointers. We made our own function pointer and called through them for the x input stuff, x input get state. And so basically that is exactly what it's doing here, but instead of having a global pointer, it actually has a global table, and it has several global tables, one for each struct that uses virtual functions. Basically what it does is it will actually look at the structure to find the pointer to the table, look up the pointer to the function in that table. It's this doubly indirected thing, and finally it will dispatch. If it sounds like a lot of extra work, it is. One of the reasons that C++ virtual functions are not fabulous is they do hit that double indirection, which is not a very good thing. It costs you some performance every time often. Depends how good the compiler is and CPU is at handling them, certainly, so the cost may vary. But it is definitely a lot different than calling just a regular function. It is not a zero-cost abstraction, as they say. Anyway, point being, that is actually what we are getting back from this DirectSound call. So back here, when we ask for DirectSound create, basically we're calling DirectSound create, and DirectSound create is going to give us back an object with that vtable in it. So you'll notice we don't have to ask, we don't have to use getProcAddress to get the rest of the functions we're going to call. Instead, we're just calling them off of the actual object that we got back, and basically the vtable that is in that object is the thing that is actually allowing us to get to these other functions. And just to be a little more explicit, you might say, well, where is that vtable in memory? Well, the vtable got mapped into memory when we loaded the DLL. So the DLL itself had the vtable in it. When it got loaded, we are actually pointing to, when we get back our handle to the struct, or I should say the DirectSound object, since we're, whether it's a struct or a class, who knows how they declared it internally. It doesn't matter for our purposes at all. Structs and classes are the same. Anyway, point being, when we get back that handle to the DirectSound, it basically has a pointer to a vtable that is inside the DirectSound DLL, and we will basically just be calling through that jump table. So every time we make a call, it'll look up in there, it'll grab out that thing, and there it'll go. And we can even, if you want to, oh, I got to save my file. If you want to, we can go ahead and even take a look at that happening. If I open up the debugger here, again, everything gets translated to CPU. It doesn't matter what language you program in. The CPU has to do everything. So no matter how fancy stuff looks in a language, basically you are always going to end up having to have the CPU do whatever work is necessary to have that happen. Languages make things sometimes simpler for the programmer. They do not make things any simpler for the CPU. That is just how that works. So basically you can take a look at this here. Let's see here. So you'll notice this is the assembly language for this call, and you will notice right here this is the part that we're looking at. So normally when we call a function, I'll just show you another example here actually, just to make it a little clearer. So normally if we went down here, and let's look at a function that we were actually, that we had implemented ourselves, right? This is a function that we had implemented ourselves. So if I go ahead and I go to the disassembly here, you will notice that basically what gets outputted is essentially a direct call to the address of that function. And what basically happened was the linker, when it linked us up, it basically said, look, that is where the function is. So that is the address I'm going to output, and the call is just a direct call to a constant address. That's what happens. There's nothing fancy going on, and it's one thing. When we call into it, then we're in the function. That's it, right? That's what happens. Now, in C++, every time you use a virtual function, you are basically incurring more overhead than that. What you are actually doing is you are going in here, and you can see that this is the call site. This is the place where we're actually going to call that set cooperative level. And as you can see, it cannot insert an actual address. It has to basically insert a call to an address that it loads. And you can see that happening right here, basically. You can see that it moving into RAX. It's basically getting the vtable pointer. It's loading in that function. This is doing the pushes for the actual, I think the actual parameters and stuff that we want. But this is actually doing a call off of RAX, which got loaded up here. So you can see that it's actually doing work to load something in. First it's loading off the RSP, then it's going ahead and actually loading off of that, which is the double indirection. Like I said, it's loading a pointer and then loading a pointer off the pointer. Excuse me. And then finally it's calling one more indirection. It's basically calling, to be more explicit, it's loading in the DirectSound, it's loading the vtable pointer out of the DirectSound, then it's loading the actual address out of that vtable because it knows this is the address, I believe. I am not the best person at assembly language. I've never written a compiler that outputs C++ assembly language, so I'm just basically assuming that this is roughly what it has to do. Now maybe if we were in optimized mode it could get this a little simpler or something like that, but basically that is the idea. So you got to load the pointer to the object, you got to load the pointer to the vtable, then you got to load the function pointer out of that, and finally you can go ahead and call it. So that's what's going on there, if that makes sense. Hopefully that's clear to everyone. It's not particularly complicated, and you don't really have to understand it because we are not going to be using anything like that in our code, but that is what happens in C++, and that is what happens in COM as well. So that's what's happening in here. We're getting back one of those. We are basically asking DirectSound for a handle to the primary buffer, and that primary buffer we are using to set the output format for our sound, which we set to be stereo, 2 channels, 16 bits per sample, which is good, and excuse me. Again, sorry, I'm so sick. And we are also saying that we essentially want to be 48 kilohertz audio, which I picked basically because I think one time I asked Jeff Roberts, who of course was the guy who maintained the Miles sound system for a very long time, what was the most common native format for sound output, and he said 48 kilohertz, so that's what I'm going with. But you could pick 44.1 as well, CD quality audio. You know that all sound cards support that as well. Pretty much has to, I think. It was just a question of whether they resample it or what they do to it. So anyway, we then open our own buffer here, and that is what we're going to talk about right now. We open a buffer called the secondary buffer, which is the buffer that we can actually write into. We can't write into the primary buffer. Those days are over. We have to write into the secondary buffer. That's the way that's supposed to work now. And basically the kernel will sort of take all the people who are writing the secondary buffers, mix them together, and output them to the sound card. We no longer get direct write privileges to the sound card. Kind of like we no longer have direct write privileges to the graphics card. It all kind of gets mitigated. It all goes through Windows. I guess if you use something like Mantle, maybe you can, but assuming that you're going through the Windows standard APIs, you don't get direct access anymore. It's just not how it works. So in here, what we basically want to do is we want to keep this buffer pointer around. This is basically the thing that we're going to use all the time to write to the sound buffer. So I'm going to basically elevate that out, this secondary buffer. I'm going to elevate that out to our globals. Again, I'm not sure that that's going to stay there necessarily because, like I said, I don't like to have too many global variables. In a platform layer, it's usually not that big a deal, actually, because you're kind of really isolated in the code here and you kind of have looked at it all. It's not that big a deal, but at the same time, you always want to be aware of it because a global variable is something that anyone can modify, and sometimes that creates a little bit of a stringiness in your code. So be aware of what you make global. Don't do it willy-nilly. Make sure you understand why it's global and that it should stay global and that there's only going to be one of them. And if any of those things aren't true, don't do it. All right, so we're going to actually create that buffer globally here. And then once we get that buffer, we will be able to output sound from now on. So in order to output sound, basically I'm going to do something extremely simple. I am just going to ask where the right pointer is, and I am going to fill in some memory with the sound. And now sound is a little bit wonky, certainly. It's a good question what we're going to put in there if we're not loading anything yet, because I wanted to wait for I'm going to show you how to load WAV files later so that we'll be able to play sound. But to get something working, first off, I think I'm going to use a good old square wave, something like that, so that we can just hear. It's going to be an awful sound, certainly, but if we take a look here, you can see basically we have a square wave. It's got a pretty reasonable graph here. These are the basic kinds of waves that you can output that are really simple to code. Obviously, there's a sine wave, there's a square wave, triangle wave, sawtooth, and they just look like this. As you can see, square is probably the simplest to code. All it is just a high signal, high positive signal, followed by a low negative signal, and nothing in between. So it's just a full-on oscillation like that, and that's about it. So I think basically that's all I'm going to try and dump into this buffer. So basically we're in our loop here, right? One of the things we do in our loop is we get the input. Then another thing we do is we render that weird gradient. So right here after the gradient, I am going to go ahead and try to lock that buffer. So I am going to go ahead and do DirectSound output test right here just to see if we have anything working. Now, in order to do that, basically what we need to do is we need to lock that DirectSound buffer. And so basically, if you remember from the help, we basically had to use the help for DirectSound 8 because the old DirectSound help wasn't even there. It's probably fine to use DirectSound 8 for any real purposes. Almost every modern machine, I think, is going to have DirectSound 8, so I wouldn't worry about that too much. But most of this stuff works in the older API as well, so I was just calling the older version, which is DirectSound 7 and prior. Microsoft doesn't even have the help for those posted anymore. But anyway, what we need to actually do is fill up the buffer. So we got to actually do a lock here. Where is our lock? There is our lock right there. Where don't they have? I need the actual help here, people. I want to actually see the help. There it is. This is what we're talking about. So this is the function that I actually wanted. Basically, what it does, if you remember, we are going to be doing circular buffer output, and I drew a diagram about this yesterday. I'm going to draw a diagram about it today again just to reinforce it. But basically what's happening here, right, is we have a thing that looks like this. It's a buffer, and we are going to write our sound into the buffer like this, right? Off it goes. And basically what happens here is DirectSound will be playing this buffer, and when it gets to the end of the buffer, it's going to loop back to the beginning. So it's just playing it over and over. So effectively, you can think of this as a circular buffer. It's like the beginning of it was copied to the end, right? It just keeps going. It's when it plays. So as it plays, it's going to just keep going as it goes off the end. If that makes sense. So what's going to happen here is we need to basically write into this buffer. And in order to write into this buffer, DirectSound actually knows that a lot of times you're using these as circular buffers. So what it allows you to do is it allows you to lock a region by giving a pointer to the beginning, basically. Not a pointer, but basically an offset, to say this is the place I want to start locking the buffer to write into. Because remember, this is a system buffer. Windows wants to know when we're writing to it. So we need to basically issue a lock call to say we're about to write into this, so just so you know, you're going to have to update it. So we locked it to write into this. and it actually gives us back 2, potentially, regions. So for example, when we lock this, we give it a size, and maybe that size was this big, right? We say that's how many bytes we wanted to write into the buffer. So it needs to lock that big. But it can't lock that big because obviously there's nothing out here, the buffer ends. So what it does is it takes this sort of residual here, this part, and it locks the beginning of the buffer for however much the overrun was. So it basically gives us back 2 regions, right? It gives us back one region here that's at the actual offset we asked for, and that goes to the end of the buffer potentially, and one that starts at the beginning of the buffer and then goes to wherever it would have been to make the buffer the size that we wanted. Now, that doesn't have to happen. It can also be that if we gave it a pointer, or rather an offset, to somewhere in the buffer where it could lock the whole thing, just in one place, right? And this is my little lock. How's that? Oh, it's awful. Don't look at that. Okay, anyway, it'll lock it all in one chunk. So we may get back just 1, we may get back 2, and we have to handle both cases, basically, from DirectSound. It's easy to do, but that's basically the idea. Hopefully that makes some sense. Okay. Let's put this up here. All right, so what we are going to try to do here, and this is where things get a little complicated, and I always mess stuff like this up. It's confusing. We need to write a little function that dumps the sawtooth into the buffer. So we're going to call this lock call here, and we are going to go ahead and call our global secondary buffer and attempt to lock it. We are going to give it the offset, and that offset is going to be something that we get from the right pointer, so that's going to be the right pointer. And we are going to try to write out, I don't know, maybe we'll basically look at the play cursor as well. We'll talk about what those two are and do it. So let's say bytes to write here. Let me see if that's actually right. It is in bytes, yes, it is. Then it is going to give us back basically a series of pointer. It's going to give us a pair of pointer and size to specify those 2 regions. So this is region 0, let's say, or I guess I called it region 1 in the diagram. So we have a pointer to region 1. We have a size of region 1. So we have region 1 size. And then we're going to have this again for a second one. And that is what we're going to pass here. So we've got region 1 size, and we're going to pass the address of both of them because it's basically returning those to us. Again, it's passing the address so it can fill them out in memory. And then we're going to pass the flags, and the flags are pretty much self-explanatory here, I guess. Yeah, there's not much. Oh, okay, so you know what? We can actually lock from the right cursor directly. All right, so we can even just do that. Although we don't really want to do it that way. We want to actually specify it, I'm pretty sure. So we're going to go ahead and say that that's the case. All right, so we don't really need any flags. As far as I can tell, there's nothing in there that's going to help us. So this is basically what we're looking at for the entirety of this call. That'll lock it for us. So now we just need, we actually need to get that right pointer, and we need to get that byte size. Right pointer, and we need the bytes to write. Let's see. Okay, so we have to actually get these from somewhere. So that's our next goal. Once we get them, we can then fill the region with a sawtooth, basically. I'm going to do that in a little bit of a sort of janky way here. Again, this is just test code. This is going to get deleted. So basically what I'm going to do is I'm just going to make this 100% explicit. I'm going to say we're going to start writing at a particular sample index, right? And that sample index is, or I should say, yeah, sample index. And that sample index is actually going to be wherever this first region actually ends up being. So yeah. Sorry, I'm not explaining this very well. This is the lack of coffee. Let me say that again. We have a sound buffer, and that sound buffer contains samples. It contains samples that look like this. It contains samples that look like this, right? They're interleaved. And basically each one of these is 16 bits, right? So it looks like this. 16-bit, it's an int16, another int16, another int16, kind of ad infinitum, right? Going on and on and on. So our buffer is 16 bits for the left channel, 16 bits for the right channel, 16 bits for the left channel, 16 bits for the right channel. So basically I want to loop over these things, and this is what we're considering a single sample, because basically they go together, right? We can't output anything less than that. We need to output one of those at a time, because that is the only thing that actually makes sense for our stereo sound. We couldn't output just 8 bits. It'd be like half of the left channel value. That doesn't make any sense. So we're going to output those at a single time. So basically, region 1 size comes back, and it had better be an even multiple of the samples, because if it's not, something really weird has happened. Because we're only going to ask for an even multiple of the samples. The buffer is only an even multiple of sample size long, and we're not going to ever give it a right pointer that isn't an even multiple. So this would be a good place for an assert. I haven't talked to you about those yet, but we will talk about those maybe in the later of the stream to assert that that's true. Assert that region 1 size is valid, and region 2 size as well, in the case where it gets returned. So we'll talk about that a little bit later. I don't want to start throwing asserts in here until I actually have a chance to sit down and talk with you about what they are. So we'll have to schedule that at some point, because it's pretty important. Anyway, sample index is 0. It goes up to the region 1 size, and then it will be finished. Now, of course, we then have to do the same thing for the next region. So we want to go up to region 2 size, and these sample indices are relative to the region, right? So these are all the samples in region 1, these are all the samples in region 2. And what we have to basically do is we have to fill in something now. So we're going to have to fill in the pointer to the buffer here. Basically, we're going to write 2 things, a left and a right each time. So the first thing we want to do is get an int16 pointer to the buffer. Now, it returned us the pointer, which was region 1, right? And so this is basically the sample out. This is what we're going to be writing to. So we're going to cast that to an int16, which is the thing we're going to be writing. And basically, we're going to write here. We're gonna write as we increment along. We're going to write our left here and our right here, right? And then we're going to do the same exact thing down here. Does that make sense? Hopefully that's clear. All right. So basically, this will do everything that we want to. We just have to figure out what we're going to do in terms of the actual values here. So what we want to do is we want to go and every sample, depending on which sample we are at, we basically want to go ahead and make a square wave. So we want to be able to basically just do, if our sample index happens to be, the first n samples, it's going to be high positive. It's the first, if it comes after that, the next n samples are going to be low and high and low and high and low. So we're going to use the mod operator for that probably. So basically what we're going to do here is we are going to actually, we don't even really need to use the mod operator. We could be a little more janky than that. So basically what we're going to do is we're going to find a variable that's going to tell us where we are in our sawtooth pattern. We are basically going to call that, not our sawtooth, our square wave pattern. We're going to call that our square wave counter. And basically all that's going to do is if the square wave counter happens to be 0, so we're done, it's basically we've finished one part of our square wave. If the square wave counter happens to be 0, we are going to set excuse me. Man, I wish I would get healthy again. I can't tell you how frustrating it is to be trying to talk to you and have this stupid cold in my way. It is really annoying. All right. Anyway, this square wave counter is going to basically go up to the number of samples that we want our square wave to have high before it goes low, and vice versa. So basically what we're going to do is we're going to say, well, if our square wave counter, I don't know, I'm going to pick a random value here and then we're going to tune it later, square wave period or something like this. We're going to reset it each time. Again, this is kind of ugly the way I'm doing this. Probably not the best way to do it, but it's the first thing I thought of. So we're going to make it do that way. And then what we're going to do is we're going to say our sample value is just going to be whether or not the square wave counter happened to be above half the square wave period. Basically, that's about it. That's all we're doing. If it happens to be above that, then it will output the highest possible value that it can. Well, maybe not the highest possible value. Let's just say 16,000. Yeah, I don't know how loud we want this thing to be. Basically, this is a 16-bit value, so 32,000 is the maximum it could be. 32, whatever it is, 65536 divided by 2. And if the square wave period, if it's not that, if it's in the other half of the square wave period, it'll output the negative. That's basically all I actually want to do here. And these are basically the exact same loop. So we'll probably compress these in a second down to one loop. But that's basically it. That is all we wanted to do. So all we really need to do now is make sure that we actually fill out all these values somewhat reasonably. I believe that's correct. Okay. Someone on the stream said, let's code a mini Moog synthesizer and emulator instead of a game. You know what? That is Sean Barrett's turf, ladies and gentlemen. I am not the person to do that for you, but you know, I bet if you asked Nothings at Twitter to do a stream where he codes a Moog synthesizer for you, I bet he would do that. That is exactly the kind of thing that he would do, and he is exactly the kind of person who would know how to do that a lot better than I would. I would just end up writing a lot of crappy code like this that I just wrote for you, because honestly, I never synthesize sound, really. I always play from some kind of sample materials that get mixed together. So this is way out of my area of expertise, to say the least. But it's definitely the easiest thing for us to write to just get things going. Okay. So we need some stuff here we have not finished, because we have to define some things. Obviously, we have a square wave period, and that square wave period is going to have to be something reasonable. We also have to make sure that we actually decrement our square wave counter every time we output a sample, right? Something like this, just so that it starts to count down to 0, as it should, and so it will repeat. Now, the square wave period, I don't really know what the average square wave period should be for a sound that you can hear. Let's say middle C. What is the frequency of middle C? Okay, so middle C is in hertz. Basically what hertz is, if you don't know what hertz is, it's cycles per second. Basically what that means, if I go back over here to our amazing diagram, basically what you can imagine is we had that square wave, right? It's going like this. And similarly, you might have a sound wave, you know, that goes like this. And basically, I believe the way they typically measure it is a cycle is how long it takes to go back to where you were. So from like one peak to the next peak, right, like this, or from here to here, basically, for one complete copy of the pattern of the wave. That is basically called a cycle. That is what we're considering a cycle. And so hertz is just cycles per second. That's all. So basically, if we are going to play a sound for 1 second or fill a buffer that's 1 second long, then you can imagine it should have 261 copies of that pattern for middle C. Basically, that is what that means. So if we try to back this out here, if we're trying to figure out what our square wave period should be, basically what the value is, maybe I'll go here and say, you know, what the hertz is. So we'll try to get a hertz, something like that. So I don't know, let's just say 256 should be close enough. I want a power of 2 just because I'm a programmer like that. That'll be somewhere close to middle C in theory, I believe. Should be fine. So if we're wanting to actually do 256 cycles per second, right? Then the question is, how many samples do we need to fill? Because again, this is going to be in samples here. How many samples do we need to fill before we actually have that many? How many samples for a full, for one of our loops? So basically what we want to do is we want to say, well, hertz is samples per second, right? So all we have to really do is say that whatever our sample rate is, and we know what it is right here, we set it, so I could even say this is our samples per second, right? That we actually asked the sound buffer for. Oops. That we actually asked the sound buffer for. There it is. Samples per second. If that is our samples per second, then we basically know that if we want to have 256 of our thing, then each one of them should occupy basically the number of samples we're actually going to do in 1 second divided by the number of the things we want in 1 second, right? Because that's how many chunks there would be. That's how many samples would be per chunk if we chunked up our full second into 256 slices. So I'm going to say that's roughly our square wave period. We're not trying to be precise here. So I'm basically going to say that that is what we will actually fill out. So now this should work, I think. We can go down. Let's see, we're writing that many samples. Yes, we are. So what we have to do here now is we have to actually turn our region sizes into counts, right? Because these are sizes, these are byte sizes that are coming back, and we actually need sample sizes. So like I said, we got to assert that they're valid, and then I jumped into an explanation and forgot to finish what I was trying to do here. We need region 1 sample count, right? Because this is how many bytes, but we know that our samples are actually 32, so that's 4 bytes per 32-bit sample, because we have 2 16-bit samples, a left and a right. So basically what we have to do is we have to divide this here by our bytes per sample, right? So by our bytes per sample to actually get the region 1 sample count, which is what we want to loop over. And the same thing here, we got to do the exact same thing down here. And the reason I wanted to do the assertion, like I was saying, is just to guarantee that what it gave us back was evenly, excuse me, was evenly divisible here. Man, I hate the winter. I get sick every year, and it is awful. Absolutely awful. I don't think I've gotten much sleep the past few nights. It is just absolutely miserable. Don't ever get sick, people. If you can avoid it, just don't do it. It's no good. God, all right. Well, anyway, the reason I made bytes per sample be a variable is because I knew it was used up here as well. This is it right here. So I figured we'd just clean this up, and now we'll actually have basically a complete set of definitions for our sound system that we could change if we wanted to, just to make it a little clearer what's going on. So we're going to init dsound with that exact parameter. Then we're going to go down here. We're going to do all the work with those parameters. And so pretty much the only thing we need to do now is we need to figure out where these guys are going to come from. I believe we caught everything else. I don't know, though. There's a lot of code in there, and I was talking the whole time, so there's probably some bugs, but we will debug them, and it will not be an issue. Okay. Finally, we basically need to figure out where we are going to ask DirectSound to write, and we're going to have to figure out how many bytes we need to write. And we have some information we can use to do that, basically. If we go back over here to our DirectSound buffer, we can see there should be a call. Let's see if I can bring up the actual definition of the buffer somewhere, people. There it is. Okay. Basically what we've got here is we've got all the calls that we can call on a buffer. And what I basically want to do is I want to get back the play cursor and the write cursor. And I'll talk about what those are. I believe it is this call right here. And this is the call that we're going to use to get that back. So right before we determine what we're going to do, I'm going to call this. We are going to assume that this succeeds, because if we can't get it, then the sound buffer died or something bad happened, and we probably shouldn't try to output sound if we can't actually get it. So I'm just going to go ahead and wrap this here right up in that so that we don't actually do anything if we can't do this. The same should be true of the lock while we're at it. The lock itself, again, returns an H result. So I'm just going to say, let's not do anything if for some reason we can't lock these buffers, because that's no good. That just means DirectSound has encountered some kind of really bad, sort of fatal error, bad condition. Maybe the sound card got yanked or changed out from under it or something, and we don't want to be doing anything in there. We might end up with bad writes or some bad stuff going on. All right. Now, what should happen here is basically we should be able to ask DirectSound for the play cursor position and the write cursor position, and I will show you what those are. Basically, those are both going to be returned to us. If this call succeeds, we will then have that information. So there we go. And that should basically compile now, I would think. Oh, right, no, we need to call that off the secondary buffer, like that. And then we just need to do these. So there we go. Now, what are these things? Well, basically what's going to happen is in our diagram here, I don't know if I can back up how far I can undo in this thing. Look at that. Look at that undo. Didn't quite get us far enough. All right, no big deal. We'll just go ahead and clear that out and start drawing again. Where's the pen tool in this thing? There it is. All right, so basically what happens here is in that buffer again. Oh my, why are we so tiny? Do I have to use the pen? No. How do I get a brush, people? Give me a brush. Is that a brush? There we go. All right, here is my buffer. There it is again. Basically what's going on here is you have to imagine that the hardware, the actual sound card, or the kernel mixer, or whoever is basically controlling the situation. We don't really know who that is, but whoever it is, they are actually looking at this buffer at a particular location. And that is the play cursor. That is the play cursor. Wow, that is a really bad drawing. Play cursor, right here. Now, because of the way hardware works, and because of the way the kernel mixing works, and all those sorts of things, it's all asynchronous, right? This is happening whether we're running or not. It's happening perhaps concurrently with us on a separate core of the processor. We may be interrupted at any time in our code because the operating system wants to do something, etc., etc. So these are things, the hardware, that sound is going to be playing whether we're running or not. And so it's not safe for us to start writing directly in there, because by the time we finish doing whatever the write is, the hardware may actually have beaten us because we may get interrupted or who knows what happens. The hardware may actually have beaten us and played garbage, something that's half written or who knows what. So instead what happens is there's another cursor called the write cursor, and that basically leads the play cursor. It's a cursor that's somewhere else out here. And basically the write cursor tells us, well, we can write into a particular location, and then we can move, basically from there forwards, right? And so what we're going to do is we're basically just going to see how far the write cursor moved, probably, and we'll write into that. Now there's something a little bit odd here. Since the lock doesn't, as far as I know, let's take a look at this, because I'm trying to remember exactly how this system works. I don't think the lock moves the write cursor, does it? Let's take a look. Blah, blah, blah. It returns the ring buffer stuff, like we said. After writing data to the pointers returned by this method, the application must immediately call unlock. Yes, that's true. So we should actually do that. We got to do that as well. The method returns write pointers only. Yeah, so that's it. So basically, this write cursor is just going to move a little bit ahead of the play cursor. It's not going to move when we write. So one of the things we're also going to have to add here is the fact that we're going to have to track where we were in the buffer, basically. And that's really all we're going to be able to, that's what we're going to have to do. So really, the write pointer is not actually going to be something that we need to know about. Basically, it's the play cursor, really, that we're going to have to see, because we're going to have to look to see where we can fill to, basically. All right. So that's fine. It's going to be a little bit more complicated math. Like I say, this code is going to be pretty janky. Hopefully, at the end of this, we'll actually be in relatively good shape. And when we actually output sound, it'll be a lot easier than this, because we'll have abstracted this kind of weird ring buffer stuff out in a way that we don't have to deal with it. So it won't be so confusing, basically. Take an almond milk hit here. Yeah, this is probably, like I said, I told you sound was going to be rough yesterday. This is the kind of stuff I was referring to. Outputting to a ring buffer is never fun. It's always a little confusing. As we boil the code down, it'll get a little clearer. At first, it's always a little janky, especially when you don't remember how everything works, which is the case with me at this point. But anyway, point being. So, basically what we want to do is we want to actually remember where we were, how many sounds we outputted, which is sort of what we're doing here. And we want to be able to lock the buffer at wherever we left off, essentially. So since we basically have a counter, we could reuse this counter. I don't know if we really want to do that. Yeah, maybe we do. So basically what we might want to do here, for example, is we might want to just use a mod. It's inefficient, but it might be a little cleaner than what we were doing, basically, to actually get this value. So let's think about it this way. Let's say that we actually have a sample index. This is our sample index here that we're going to write to. And that's going to actually loop. We want that to be an unsigned integer because we want it to, basically, if it ever wraps over 4 billion, we want it to go back to 0, not to a negative number. So we're going to have a sample index here, basically, and that sample index is just going to go up forever for now. That's what we're going to say. And we're going to get rid of our square root of counter. So we're going to have a sample index, and that's just going to go up forever. It starts at 0 and goes up forever. So the first thing that we're going to do to write into the buffer, basically, is when we lock the buffer, we're actually just going to lock the buffer at whatever our sample index is, our global sample index. So this is going to be, I don't know what we're going to call this, actually. I guess let's see. Let's call this our running sample index. So it's just where it just keeps going like that. So basically what we're going to do here is we're going to say, okay, we've got this running sample index, and it's going to just keep going up forever to tell us roughly where we are. We're then going to say, okay, we need to know where in the buffer that would be, because this is basically just going to go up forever, and we want to map it into the circular buffer, if that makes sense. So basically, we want to make a D word that is basically the sample index to lock. So this is the sample index to lock. Is going to be the running sample index times the bytes per sample. So that turns it from a sample index into a byte sample. And so I should actually say this is the bytes to lock. Turns it into where in the bytes it was. But we now have to mod by the size of the buffer, basically to say if it loops, when it gets to the end, it's got to go back to the beginning because it's in this circular buffer, right? Now the mod is basically just says remainder. It basically says divide this number by this other number and give me the remainder, which is exactly what we want, right? We basically want it to give us something back that's going to be, excuse me, that's going to be whatever fractional portion we would have of the total buffer size, because that's where in the buffer we will actually be. So that's what we actually want here. We want that byte to lock. So that is what we'll be asking, byte to lock right there, right? And then the number of bytes to write is basically going to be however far we would go to get to the play cursor, because we don't want to write past the play cursor. So we're just going to write from wherever we are to the play cursor. So basically, here we go. We have got our bytes to write. And basically what we need to know is we need to know whether the play cursor is in front of or behind the byte to lock. So basically, if the byte to lock is actually in front of, right, the play cursor, if it's higher than where the play cursor is, because this play cursor, again, is also going to be in bytes, I believe. Let's verify that. I don't actually know. We didn't look. Let's take a look. Address of the variable that returns the offset in bytes. That's what we want to know. So basically, if the byte to lock is above the play cursor, that means we have to write all the way to the end of the buffer and then from the beginning to the play cursor. So basically, that means that our bytes to write, which is what we're trying to compute here, our bytes to write is basically going to be the buffer size, right? So this is the, I should say, secondary buffer size, just so we're clear about this. The secondary buffer size minus wherever the byte to lock is. That's how far we had to go. Again, to go back to the diagram, basically, I know this sounds complicated and there's tons of finicky math in here, but not really, it's arithmetic, really. Basically, what I'm saying is we've got two cases. In fact, let me go ahead and clear that out so I can show the two cases. So basically, we have case 1 and case 2, and we got to handle both of them. So in one case, this is our byte to write here, right? And here was the play cursor. This is byte to write, not the right cursor. The right cursor is somewhere in here, but we're ignoring the right cursor. We don't even care where it is. So what I'm saying is, if this is our byte to write, and we see that the play cursor is here, then we know that it's safe to fill this part of the buffer and this part of the buffer. And this is the region we don't want to touch, because basically anywhere in here we don't want to touch, because we already wrote it and the play cursor is still hasn't played that part yet, if that makes sense. So basically what we're going to do is we're going to look at this and we're going to say, okay, if the byte to write basically is greater than the play cursor, right? If it's greater than it, then we need to do two chunks, that chunk and this chunk. On the other hand, if the opposite was true, if here's the byte to write, this is our byte to write, and this is our play cursor, then we only have one chunk. We only have this chunk here, right? This is case 2. So if case 1, case 2. Hopefully that makes some sense. That is what I'm trying to write here. So basically, this is the case. This is that case 1 at the top when byte to lock is above the play cursor. Basically, what we need to do is we need to take the secondary buffer size, so the total buffer size, which is, you know, this whole thing here. We're taking that total buffer size and we're subtracting this value from it, so that we're just producing that number right there, right? And then we also need to add the part at the beginning of the buffer. So we're basically going to add wherever that play cursor was, because we got to play from 0 to that, right? Makes some sense. On the other hand, if they're the other way around, then we just have a very simple thing to do, which is say however far is between those two cursors is how much we're going to write. That is how much we're going to write. So that's what we go in here and we do the lock. We do the lock with that bytes to write, and then what we do is we basically say, okay, our square wave counter is still in effect, but actually, I guess, like I said, we could get rid of that with a mod. I'll show you how to do that in 1 second. Basically, this is all about modding. Maybe we should have a little discussion about modding in the Q&A. Since we never really covered modding, we'll talk about it in a little more detail. It's kind of something that's interesting to know. So basically, we are going to go in here, and we are going to do the to-region thing, like that, like we wanted to. There we go. And we will be writing our stuff as we wanted to. And then so the only thing we have to do is change our sample value to basically be this if statement. Instead, is just going to be on our square wave period, our running sample count, our sample index rather, mod the square wave period should basically be what we want to do. Is that correct? No, sorry, divided by the square wave period, divided by 2. Yeah. Oh man, this is a little nuts, but I think that's it. If the running sample index divided by half the period, that's either going to be 0 or 1. So we got to mod that. Yeah, that's a little annoying. So I'm going to make a secondary variable for that, and then I'll explain it, assuming that I did it right. We want the half square wave period. Half square wave period equals square wave period divided by 2. There we go. And so all I'm trying to do here is basically just say, so if we have we divide this out by half the square wave period, then basically what we're going to get is which half period we're on, right? Basically, if I have a sample index and it's going up and I divide it by half the period, we're going to say it's going to be 0 in the first half period, 1 in the next one, then 2 in the next one, then 3 in the next one. So basically, if you imagine what I'm doing with that divide, if this is our square wave, right? Basically, you can imagine what I'm doing is dividing by half the period. This is half the period, right? This is half period here. I'm dividing by that. So that basically what that'll give me back is just an integer that counts up for which half period I'm in. It'll go 0, 1, 2, 3, 4, 5, 6, and so on, right? So all I have to then do is look if the number is even, right? If the number is even, we should be high. If it's negative, we should be low, or vice versa. We don't care which phase our thing is. So basically what I got to do there is I got to mod it by 2. I got to take the mod 2, which says basically 0 or 1, whatever the remainder is when you divide by 2, that is the thing that's going to be it. Oops, this is actually, just goes back in there. So that's what I'm trying to do here. There you go. And that should be just about it. The buffer size, again, we got to actually put in here because that's used now, secondary buffer size. And we already, again, compute that right there, secondary buffer size. And you'll notice that a lot of these things kind of work themselves out. Again, this is why I always say compression-oriented programming is the best way to do things. You'll note that basically all I do when I'm trying to write code that's somewhat complicated like this, and that's sort of finicky, is I just keep writing whatever the most obvious thing is to write at the time. I don't try to overthink it, and then the patterns just kind of emerge. You can see everything here. In fact, you can even see where we're going to go with this eventually. You can see how these two loops are the same, so we'll probably boil that down and so on. And basically, you just keep pulling stuff out that's common. That is the best way to end up with nice working code that does exactly what you wanted to do instead of trying to front load it. Okay, I got to blow my nose here, people. I am awfully sick today. I apologize. Man. I would like to spare you from that on the stream, but there's really not much I can do about it. That's just the way it goes. It's awful. It is awful. All right. Let's see here. I think we've basically done everything, but let's just do a quick spot check because there are probably some bugs in this given how many things happened here. Let's just do a quick once over just so we understand everything that we're trying to do, and then we'll go debug it. So basically, we basically made our hertz here. I'm going to call this our tone hertz because it's basically saying our tone samples per second. Whoever in the screen that says gross, it is totally true. It's awfully gross. I have to live with it. I have to live with it, man. That is the thing. I've been living with this for like a week. It's awful. The cautionary tale, do not get sick, people. That is what I'm telling you. Do not get sick. I'm hoping maybe I'll start feeling better later today or tomorrow. It's been a long time. All right, anyway, this is our sound stuff here. This was for our graphics test, and this is for our sound test. They are not similar at all. Okay, sound test. So we have our samples per second. That's 48 kilohertz. That's how many we're playing. We have our tone hertz. And that's tones per, this is per second as well. We might want to call this sample hertz, but I don't know. It's 6 of one, half dozen the other. Our tone hertz is basically 256. So we are taking our samples per second and dividing that by the tone hertz. That's how many we want. We have a half square wave period, which is going to be whatever that period is divided by 2, and that's because we want to know ups and downs, so we want to be able to divide by that. We have our bytes per sample, which basically tells us how many bytes we take to write one left-right pair, each at 16 bits. So that's times 2, 16 bits. We have a secondary buffer size, which is however many samples per second times the bytes per sample, because we know we have a 1-second buffer. That's basically what we define it to be. So we init DirectSound with that, and that should be basically everything that we needed there. I'm going to double check the Win32 inits dsound function to make sure that that is what that takes, samples per second and buffer size. That's good. That all works. All right, so we then come in here, and now we actually do all the craziness. We ask where the play cursor and the right cursor is, even though we don't actually care where the right cursor is. So we ask where the play cursor is, essentially, and let's make sure we have those in the right order. Yep, play cursor first, so that's good. We then get the byte to lock by taking however many samples we are in. There's the thing we forgot. I knew we forgot something, plus running sample index. We got to add that every time through. So we take our running sample index, we multiply that by the bytes per sample to basically get where we are in the running bytes. So basically an infinitely increasing until we wrap the actual value, the actual variable an infinitely increasing value of bytes. So then we use the mod to map that into the secondary buffer where we are in the actual buffer, because remember it's kind of this circular buffer thing, so we need to take this long linear thing and wrap it into an actual buffer. We then say if the byte to lock was after the play cursor, then we take two pieces. We're basically going to do two locks. We're basically going to have to fill two regions. We're going to fill the secondary buffer size minus the bytes to lock, and then we're going to fill the play cursor's worth from the beginning of the play cursor's worth. Otherwise, we just fill the distance in between them. That seems totally reasonable. We then go through here, and we ask to lock exactly that. So we should get back, in case 1, we'll get, 5-minute warning, almost there. We should get back either the 2 chunks in this case or the 1 chunk in this other case. Assuming that we do get them back, we then go ahead and we figure out what the region sample counts are. We point to the first region here. Let's do it this way, just to make that a little clearer. We point to the first region. We find out how many bytes, how many samples we got to fill for that one. We go ahead here and we actually loop through all of those samples. We add to the running sample index each time. In fact, we could even stick that right in there. Make that a little clearer that that's only getting used just in that one place. There we go. We write out both a left and right value. They are exactly the same, so that's good. We go ahead and do the divide by the half square wave period, check the mod with 2, and that looks pretty good. So I don't know, we could try to run this, and I have no idea what will happen, but we can certainly try to run it. So let's take a look here and see. Okay. Well, there is one more thing we have to do before we can test it. That may have worked just fine. We have to actually start the sound playing. So that's one thing, because we never actually told the buffer. We're filling the buffer, but we never actually played the sound. So we will actually have to also do this one more thing here, which is to actually start the buffer playing. So we're going to go ahead and start the buffer playing, and we can basically do that at any time. Normally we'd want to fill the buffer first before we start playing it, but for testing purposes, let's just go ahead and do it right here. But later we'll kind of have to see maybe how to do that a little bit better. So reserved, we have to pass 0 because, all right, I don't know why. There's some reserved value you pass first. The priority, I don't think we care about that at all, basically. We don't care about priority because we are only playing one sound. That is only if you're playing lots of sound and letting it mix them or something like this. I don't think we care about that at all. We are going to loop this buffer. We want it to basically play forever, so we're going to loop it. Is there any other flags that we need? Let's see. We don't care about that. We don't care about any of that. So I think we're pretty much good to go. We will just go ahead and start that sound playing. Secondary buffer. Global secondary buffer. There we go. And let's see here. Do we hear it? Wow. Well, the square wave works, ladies and gentlemen. That much was clear. That was extremely loud in my ear. I think we're going to go ahead and maybe, I don't know if I should turn down my sound here, or if I should just go ahead and make this, let's make the volume a parameter. Holy cow. That was a little jarring. I don't know how loud it was for the folks at home, but for me, it was a bit loud. The good news is it does sound like it worked, although who knows, we could still have some bugs in there. But the basic things seem to work. I'm going to go ahead and set that to be a little bit lower. That square wave was extremely loud. Let's just say maybe 6,000, something like that. That seems a little bit easier on the ears. So that does not sound quite right to me. I think we still have a bug in there. I can basically hear a clicking over. Let me double check that I actually put out the tone volume correctly. Yeah, there we go. Let's see here. Let me make that just even a little bit quieter still, just to not blow out eardrums at all. That is still awfully loud. I do not know. I wonder if we have a bug that is actually causing it to be louder than it should be. That's an interesting question as well. All right. Well, anyway, I think we've got a bug here. So I think, what should we do? I think we only have a minute left. So I think basically what we're going to do is we're basically going to mark this as buggy, and we're going to debug it tomorrow because that, I think, is the sanest thing to actually do, would be my guess. What is the stream saying? Oh, what about unlocking the buffer? Yes, that's right. We forgot that as well. Duh. It's hard to remember everything when you're on the stream, ladies and gentlemen. Unlocking the buffer. We do need to do that. I think all we passed, yeah, we just passed exactly what we passed before. So maybe that is the only problem. I doubt it, but I think we've got another problem as well. But if we were lucky, it could be that it was just that we weren't unlocking the buffer and DirectSound was getting confused, but I don't think that's it. I think that was definitely a bug as well, so we definitely want to do that. It's just, I don't think that's our only problem. Okay, there we go. Well, no, that actually does sound right. All right, that's good. That may have just been all when I said we have to unlock the buffer and then didn't unlock the buffer, that may have been one of our only problems. I don't actually know. I'm going to say more strenuous test here. We should probably look at that buffer, verify that it looks like what we think it should look like, things like that. But for now, it does look like we were basically able to make it actually work properly, I think. On the stream, Steel Golem says, I created a new variable but then didn't set anything equal to it. I'm not sure what you mean by that. I probably just dropped one in here and then didn't actually use it, I guess. I'm not sure where you're talking about. But I guess we're going to go into the Q&A here in a second, so maybe we can talk about that. All right, that was actually pretty productive. We actually have sound output now. This is basically all, I mean, like I said, I want to test this a little more to make sure sound is very finicky, and you want to make sure you're doing everything just so. But basically, we've got the essentials down for actually outputting sound through DirectSound. This would allow us to output basically anything that we wanted to output. Effectively, we could just go ahead and output music right now if we wanted to. We could write a wave, from a wave file into here, and we would get full sound output. So we have basically done everything that we need for our sound output. Where is let's see here. It's still super loud compared to voice on the stream. Yeah, we should actually, now that we actually have sound, I need to go in there and adjust the sound volume on stream. We'll do that. We'll definitely do that so that I can talk over it as necessary. Sound volume on stream. So that'll be good. Tone volume. Let's see here. Steel Golem. Int16 tone volume equals 4,000. This, you're talking about this thing? I don't know. Tone volume gets used, right? There it is. It's set to 3,000 and then it gets used right here. That's what I thought it was supposed to be. Yeah, there you go. So anyway, that is the end of today's Handmade Hero. We will now be taking questions for 30 minutes. I guess I will be taking questions. There's no one else here to answer them. You will be asking questions and I'll be taking them, so we will be doing questions. But I think that was pretty productive. That is some very finicky code to write, doing the circular buffer stuff. I would love to go over it here in the Q&A. Maybe we'll take a few minutes just to kind of talk about this a little bit more detailed, because I kind of had to back through it as we kind of wrote out the code and go, okay, I think I'm going to do it like this, I think I'm going to do it like that. The other thing I'm going to do here is I'm going to say to do collapse these two loops, because they're the same. So that should be pretty easy to do too next time. So basically, yeah, we'll go ahead and do Q&A here, but for a minute, I just want to kind of go through and just really reinforce kind of what happened here. Especially this part maybe right here, which we didn't cover in too much detail. Let me just draw one more diagram for you, now that we actually have the diagrams working, for some definition of working. I don't want to say it too strenuously. So basically what we wanted to do, right, is we want to output this wave, right? This is what I was trying to output, just a basic old square wave, but you can imagine that this is going to get more complicated over time, because we're basically going to output real waves to it. And so basically this exact code is exactly what we're going to do to output the music for the game and the sounds for the game. It's all the same. We're just going to be outputting a different wave. Instead of a square wave, we're going to be outputting basically the output of our mixer, which is basically going to take WAV files, bring them together, and mix them together, and then eventually compress some kind of compressed sound format, but that's much later. Okay, so basically if you imagine we're trying to output this, but then we've got a buffer. Let's say this right here, let's say this is 5 seconds long, right? It's 5 seconds long, but we have a buffer, and our buffer, right, is only 1 second long, right? So basically, we have to fit this into this, and that's obviously not possible. So what we're doing is we're essentially mapping, we're going to start DirectSound playing this buffer, and what we're doing is we're essentially mapping this sound, right? The first chunk maps directly to the buffer when we write it, so we write that in there. But then we have to wait, and as DirectSound plays more of it, like as the DirectSound gets to here, let's say, we kind of come through, we lock the buffer, and what, you know, it's got still some of the square wave in here. And it ends right there, so it's actually, well, I guess it should actually end. I should try to draw that actually like it actually looks. Might be a little clearer. Let's try that. So basically, if you imagine, right, it has copied this part in there, and it's playing that part still. We now want to keep playing at this part, but we're at the end of the buffer, so when we have room at the beginning, when DirectSound finishes playing out of this part and it's done with it, we are going to copy this part, right? We're going to put that in here so that the sound continues, right? Does that make sense? So basically what we're doing is we're just mapping parts of this, we're copying them into the right places in the buffer so that we're essentially mapping a long linear thing into a rolling circular thing by just putting in however much right behind as DirectSound reads it. We're just putting in new stuff behind there so that as it comes back around again, it gets the new stuff. So the mod operator, which is mod, or you can think of it as taking the remainder, right? The reason that I wanted to do that is because basically if we divide some point, if we have some place, right, in here, let's say an arbitrary point in here, and we divide it by the size of this buffer, right, what we will get is the remainder of that division, right? And the division, the whole number part of the division, right? If we do that division, you imagine you do that division, and you're going to get back the whole number part is going to be 0, 1, 2, 3, depending on how many full buffer lengths you were in. So if you were one full buffer length in, the whole number part of the division would be 1, right? But the remainder part of the integer division will be how many bytes in you were in that region, in that whole number region, which is exactly what we want. The mod gives us where we are relative to some whole number region that is defined by the terms of the mod. So if we do basically some index, this is our index. If we do an index mod the size, right? Then what that gives us back is it gives us a relative index. It's basically a thing that turns an absolute index, this is an absolute index, into a relative index, and that's what we wanted. So hopefully that makes some sense, and and you can understand what's going on with that mod. Now the mod showed up again, and it was used in exactly the same way. Basically we had, oops, that's no good. It always resets me to being the selection rectangle when I clear everything, which I didn't want. Anyway, basically the other thing that I wanted to do, that I used the mod for, is you can remember I did this, right? And I said I want to know whether to output this value, like I wanted to know whether the positive value, this again is the 0 line running through here, or if I wanted to do the negative value. Which one did I want to do, right? Positive or negative tone. And so basically what I did there is I said, well, okay, whatever our period is, whatever our frequency is that we want to output, I think we called that 256 hertz, basically. Whatever our number of samples is here, we basically computed using 256 hertz, we computed the samples basically per whole oscillation, right? And then I said, well, let's take the half of that. We took a half of that, right? Well, the half of that, again, just does that same relative thing. Basically what we're doing is we're saying, where are we in terms of half periods? So basically an absolute sample index, a sample index, right, modded by the half period, is going to give us a whole number which corresponds to which one of these buckets we're actually in, right? So what I wanted to do, oh sorry, not that, divided by. So if the sample index divided by the half period gives me the whole number. I didn't want the mod yet, I just wanted that, right? It's the opposite of the thing we did in the previous one where we just wanted the remainder. Here we actually want the whole number, 0, 1, 2, 3, 4. So as this goes up, we basically just have a number that counts up that tells us which half period we're in. So what the mod then does, mod 2, basically just says Well, what's the remainder when this is divided by 2? Well, the remainder when it's divided by 2, 0 divided by 2, right, is going to give us 0. 1 divided by 2 is going to give us 0. 2 divided by 2, right, is going to give us 1, and so on, right? That's how that's going to work. And the remainder of that division is what we will get when we ask the mod. So what's the remainder when we do 0, when we do this? It's going to be 0. What's the remainder when we do 1 divided by 2? Well, it's 1. What's the remainder here? It's 0, right? And that keeps going, and it basically just oscillates 0, 1, 0, 1, 0, 1. Now, someone on the chat said, could you just look at the low bit? And the answer is yes, and not only is it yes, but that is exactly, I believe, what the optimizer would do here. I don't actually know if that's true because there may be some mod rules that forces it not to do that. If this was performance critical code, you would probably write it directly as and 1, basically, to look at what that low bit actually is, if you actually care. But this is not, this is just test code. So we use mod because that's the logical operation you're doing, and I'd rather show you the logical operation. But yes, and 1 and mod 2 are the same for these values. Okay, hopefully that's relatively clear what's going on, and everyone sort of roughly follows that. Now we will go ahead and go to the question and answers. Please remember to prefix your question with @cmuratori so I can see it. Let's take a look. Let's see. Looks like I answered most of these. Sorry, just taking a second to scan through all the questions that have already built up. How will the schedule look in the future? Will this amazingly Europe-friendly time be in its place at other times? Yes, every Friday at least will be Europe-friendly. That is the goal. Why don't we use Xaudio 2? Because it does not support older platforms. That is why. I want to make sure we actually run on Windows XP. Not because I think you need to run on Windows XP. I think it's down to like less than 10% of all computers right now. So I'm not trying to push XP compatibility on anybody. You probably can start with Windows Vista and just say Vista and up is fine. Which I don't know if Xaudio 2 even works on Vista. So that might be actually a legitimate reason why you might not want to use Xaudio 2. I'm not sure where Xaudio 2 works necessarily. But basically what I want to make sure we do is on a default install of Windows XP, we should run. And the reason I want to do that is to show you how to get used to thinking about installing and running properly without forcing the user to go download 10 million drivers and installing all these different things, because you don't actually need to do most of that if you just write your code sensibly. So it's just as an exercise we're going to do that. So we're not using anything that wasn't on XP. Since DirectSound works totally fine, like as you can see, we've got sound output, we're pretty much done. There wasn't that much to it. There's really no reason to go use Xaudio. Maybe you could get lower latency with it. I don't know what the deal is with that stuff. But honestly, there really isn't much reason to go use Xaudio 2. It's just kind of a waste of time and makes you less compatible. So I don't actually really know that there's any reason to use it. But if you want to use it, go right ahead. I am using DirectSound because I want to make sure we can do XP compatibility as an exercise. Are we going to factor sound playing it into a separate function? It will actually be more than one function, but yes. Let's see here. 1 mod 2 is 1, not 0. That is what I wrote. This is the line I wrote. I said 1 divided by 2 is 0, and the remainder is 1. That is what I wrote here, and that is correct. This is the mod line. This is the divide line. This is the result of the divide. This is the result of the mod. So these go up, basically, right? 3 divided by 2 is still going to be 1. 4 divided by 2 is going to be 2. So basically, when you divide by 2, you go up. Every time you increment the thing you're dividing by, you go up. Every other one, you go up by 1. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And the mod oscillates 0, 1, 0, 1, 0, 1. Let's see. Why don't I name the secondary buffer sound buffer or something? I might in the future. Again, it doesn't really matter. That platform code is going to be so tiny, there's just not that much to it, and it's just buried in the it'll just live in the Win32 handmade file. You don't really have to worry too much about it. The platform, the bulk of the game, the entirety of the code really, will never see any of those variables or know about them at all. Is there a particular reason? X-Audio 2 is supported on XP. No, it is not. That is not true. You could install it possibly on XP, but I'm talking about the default install of XP did not come with X-Audio 2. I'm 99% sure of that. So if you have a vanilla install of XP and you try to run your game on it with X-Audio, it will not work. You will have to force the user to install X-Audio drivers in order to get that to work. I am pretty positive of that. If I'm wrong, someone could correct me in email later, and we'll catch up with it tomorrow. But I'm pretty much positive that a vanilla install of XP, no X-Audio 2. Is there a particular reason why we use the keyboard input events instead of polling? No, there isn't a particular reason other than the fact that the keyboard events are going to be, we're not going to miss anything. If we poll the keyboard, we might miss a keyboard event. Whereas if we just use the keyboard events, we know that the operating system already got as many as it possibly could because it's already polling the keyboard itself internally and getting that stuff, as far as I know. And so I think we pretty much want to just use the events because they're going to be more accurate than polling. Will we be able to remap the keys over the GUI or config file? Maybe. It depends. I don't love remappable keys. I don't love them. We might. We will definitely support multiple key layouts, though, at least for people in France whose WASD keys are different. If I understand correctly, a larger primary buffer means a longer latency between writing sound to the buffer and actually being heard. No, that is not true. So the size of the primary buffer has nothing to do with the latency. And the reason for that is because we're writing into the buffer wherever we want. So basically, let's go over the diagram one more time, just so we're clear on what's happening here. If this is, and primary buffer is the wrong thing to say necessarily. Oh, okay, well actually maybe that's, all right. So when you say size of the primary buffer, we aren't setting the size of the primary buffer. So did you mean secondary buffer, or do you actually mean setting the size of the primary buffer? Do you, who asked that question? It's hard for me to keep track of things on the, okay. 2N3053. Which buffer were you talking about? Can you tell me which buffer you were talking about? I'll answer some other questions. If you could go ahead and tell me 2N3053, which buffer you were talking about specifically, just clarify your question a little bit so I make sure I answer the right one. Will we be writing filters like reverb or what have you? We could. I rarely use stuff like that. When I'm actually doing stuff, I prefer to, especially in a 2D game, it doesn't make a whole lot of sense, but we could write a reverb filter just to show how it's done. And I could even ask Jeff for some advice on that, since he's probably the person who's worked with those the most, if he has any words of wisdom. Will we refactor the code into separate files? Of course, yes. Let's see. What causes the slight hiccup in the sound every couple seconds? So I think, I'm not actually getting that. Let's see here. I'm not getting the hiccup. Are you getting a hiccup? We were having a hiccup because of the unlock. We weren't calling unlock, so we were just erroneously using it. We were getting a hiccup. So I don't actually know if there is a hiccup in there currently. Like I said, we're going to test this a little bit more tomorrow, but I'm not sure. Let's see. It takes about a second for sound to start playing. Is that acceptable? Yeah, well, so basically what's happening there is, again, we're not actually, I could actually show you this a little bit more specifically. So what we could do, if we wanted to, is we could actually fill the buffer first and then start it playing. Basically, we could do something more like this, right? Well, I'll just go ahead and show you. So let's say we did a thing here that said sound is playing equals false, or something like this, right? Or you know what, I don't even need to do that. I can just do this. I'm going to just go ahead and get this part here. I'm going to go ahead and extract this out into a separate function, basically. Well, that'll take too long for a Q&A. That's what we should do, but I'm going to go, I'll do the original thing first. So let's say I do sound is playing here equals false. Then I come through here, and I actually do this sound play thing after the first time. So if not sound is playing, then we play it. Sound is playing equals true. So we start out false, like that. So we start out without the sound playing, and then I'm going to go in here, and I'm going to take a quick look at what we get back and what we fill. So let's go through here. So let's see here. We get back, what is our play cursor? Play cursor is 0. We are going to look at how many bytes to write. How many bytes to write is 0 as well. Oh, so this is because they are equal to each other. That looks like a bit of a bug. It should never actually happen in practice, but in the case where they are equal, they're both 0 and 0, or if it happens to happen in that particular sense, that means we've ended up in basic yes. So what I think we should do here, just to handle the case where things have gone pear-shaped, as they say, in the UK, I believe, we should probably handle the case where they're equal. They should never be equal in normal, because we're always supposed to be writing ahead of things. But when we first start up, they will both be 0. So we'll say that the bytes to write is the whole buffer, basically. But in the case that they should actually collapse down in a bad situation in the actual game, we probably would want to handle something like that as well. So now let's take a look at what happens here when we come through. First time through, they're both equal, so we fill the whole buffer. That is what we wanted, and then we start the sound playing. Okay, so in theory, that should be the whole thing. Not a very good sound, I will say that. So I suspect we still have some bugs in the thing. Like I said, I don't want to debug it now because I want to show how to actually go through and debug it, because I think we still have some bugs in here in terms of how we're filling. But as you can see, the sound now starts basically instantaneously, if that makes sense. And the reason for that was just that what we were doing first is we were starting the sound playing before we actually filled any of it. And so basically what happens there is we would be writing into essentially the wrong place. Like we have to wait till it kind of loops around again before we would actually be playing it. So it's got this kind of gap between the play cursor and the write cursor and where we're writing. That problem essentially will cause it so that we're going to have dead time when it initially starts up. So yeah, if we fill the buffer first, then start playing, and then always ensure that we're writing ahead of it, that is how to make the sound start immediately. But like I said, I think we've still got a bug in here, so I wouldn't worry too much about this yet. Don't play with this too extensively unless you want to start debugging it yourself, because I think we still have a bug in here in terms of where we're filling. One of the things that's always been true for me when writing the circular buffer code is I always write it wrong the first time, because there's so many things at play and so many different offsets, and oh, you use the sample index instead of the regular. It's just very finicky. And so what you want to do is you actually want to go and be very certain, check everything, and actually, if you can, like draw it out and verify, like, okay, we're actually writing to where we think we're writing, we're doing the right thing everywhere. That's very important, and we haven't done that yet, so I think we probably just have some bugs in here as well. And I think if we were to use a sine wave, we probably would see that as well. We would hear it more distinctly. So I think this is probably buggy, so let's just say that it's buggy. I don't want to go into it until tomorrow. Yes, okay, we will do a sine wave tomorrow as well. I didn't want to talk about floating point yet, and you do need to do that, but maybe tomorrow will be our time that we introduce that. So we'll just say switch to a sine wave. Let's see. What is the acceptable latency for games? How far in advance of the read pointer should we write? That is a very good question. And the answer is it depends. It's very difficult to actually figure out. On some platforms, like on Mac, you can do it exactly because they will tell you when your video frames will actually be displayed out the HDMI port, or whatever. So you can actually make sure that your audio is hard synced. But on Windows, at least on Windows XP, I don't know if they've actually finally fixed this in Windows 7 or 8. I don't think it was fixed as of 7. So maybe in 8, I don't really know. Excuse me. Wow, I'm dying here, people. All right. Basically, on Windows, you have this kind of slop in terms of audio sync that's really confusing, and I hate it. I really wish that they hadn't had this, that they had done it right in DirectSound originally, but they didn't. So like maybe like with X Audio 2, like you were saying, I haven't looked at that myself, but maybe with like newer audio APIs, there's something you can do. But in the old days, there wasn't very much you could do. Basically, what happens is, if you can imagine, this is let's clear this out here so you just know I'm not referring to the old buffer. But basically, this is time. Okay. Time is on the axis here, the x-axis. Time is running forwards. It's inescapable. Entropy, ladies and gentlemen. Anyway, time is going forwards, and you have to imagine basically like, here's the startup of the game, right? We get called, and then we have a bunch of startup code to do, so there's work here that gets done, right? And there's nothing you can do about that. We're like initializing some stuff. We're opening DirectSound and direct input, or who knows what else we're opening. We're getting stuff set up. At some point, we start to work on the first frame, right? So in here, this is the work for frame 1, right? We're actually doing the work for frame 1. So this is us doing work. And that work involves outputting two things. It involves outputting the sound, and the picture. That's what we need to do. So we need a sound and the picture, right? So we are then going to tell Windows to play the sound that we outputted and show the picture that we outputted, right? But the problem is, even if we're doing this on some regular granularity, like let's say this right here is 1/60th of a second, right? We can try and sometimes succeed to get Windows to display the picture right here at the 60th of a second boundary. And then here's another 60th of a second, right? Here's another 60th of a second. And we want to keep that locked frame rate, let's say. So we might be able to, if the vertical retrace, we can use what's called a v-blank potentially, to possibly have Windows show the new frame here so that the person is looking at the frame. Here's for this duration. So this is picture 0, right? And we were producing picture 0 here. Now sound 0 is a chunk of sound that ideally would go right here, right? That's where we actually want it. We want our sound that we outputted to perfectly coincide with the picture. And then when we generate, sometime after this, we're going to start working on sound 1 and picture 1 instead of 0, right? And those we want Windows to show here, right? Oops, there's the 60th of a second boundary. So we want picture 1 here, and we want sound 1 to go here, right? But the problem is, we don't really have any way of telling Windows to place the sound buffer so that it perfectly coincides with when the picture flips, right? That is the problem. So we don't really know where this is. So your question of how much latency should we have? Well, the answer is we actually ideally would have exactly the right latency such that whenever we wrote to the sound buffer, let's say the write occurred right here, the latency would be however long it was in between that write and when the picture shows up. That's the latency we want, right? But there's no way to get that. On core audio, like I said, there is a way to get that. There's actually ways you can, I think, get called back with specific things that would allow you to do that sync. But I don't think there is on certainly not on XP. I don't think even on Windows 7, maybe on 8. I don't really know. I could be wrong about that, but basically certainly going through DirectSound, there's nothing you can do. So you just kind of have to estimate it. That's why games often today, I think, ship with those weird latency estimators, because you've got that problem. Like if you use Guitar Hero, they've got those latency estimators. You got that problem. And then you've even got another problem, which is even if you got all of this correct, you have yet another problem, which is your HDTV pile of poo, let's say, right? Your HDTV, which is not fabulous, is like, that could buffer frames as well. There may be a delay even when they go out the wire. And furthermore, you may have some audio receiver that's also introducing delay or who knows what. So basically, this stuff goes out to here and potentially gets further delayed differently depending on if the audio is going through a separate path than the TV or what's going on. It's a nightmare. So actually, the saying how much latency you want, quote unquote, is really it's bad. I have been complaining about this for about a decade. I have been complaining about this, and I have told everyone who ever had an ear to listen that they need to fix this stuff, and what should actually happen is basically the OpenGL driver. What I actually want, well, just a little bit of a tangent here. The OpenGL driver should just take a sound buffers, and the sound buffers should just go out with the frames. And then it should just be mandatory. There should be some seal. There should be like a little seal that comes on your TV. There should be like this little seal, right? Like this, that comes on the TV that says, you know, not crappy, right? Or basically like, maybe it's basically a thing that says poop sauce, like this, with a little line through it. So you get a thing on your television that says no poop sauce, and then you know that whoever made that TV had it certified that they don't delay anything. They play it exactly. And that way you would know that your buffers and your frames always went out exactly together, and then they were actually displayed by your HDTV and put out through the speakers of the HDTV at the exact same time. So you'd at least know, for gamers who buy an HDTV or a monitor that has audio out, if it had the no poop sauce logo on it, that you would actually get no poop sauce. And I don't actually understand why this isn't done. I feel like someone should do it. I feel like gamers would want this. I feel like the types of people who go out and spend $5,000 on a gaming rig, the last thing they want is to have this sort of like worse, you know, they don't want these sort of bad correlations and having their sound not be perfectly synced to their game. That's ridiculous. So I would think everyone would want to get the no poop sauce logo for a serious gaming rig. I mean, it just seems to me like it would be a no-brainer, and I feel like that's a value add if you're selling products. I feel like the no poop sauce logo would be really important. So I don't know. I have advocated this for many years in the industry. Nobody cared, and so the answer to how much latency you want is nobody knows. It's completely unknown, and it's so unknown even that even on an operating system that does it correctly, like Mac OS 10, you still don't know, because the thing that you output to has latency that you can't predict. So even if you get it so that your HDMI output is perfectly synced on the wire, it doesn't matter. Let's see here. So I think we are done for the day. That's the end of the Q&A. Like I said, if you did have a question, I'm sorry if I didn't get to it. We will be debugging the sound tomorrow. And so when we debug the sound tomorrow, you can just hold those questions. It'll be the same time tomorrow, 11 a.m. Ask the question in the Q&A tomorrow, and we will go over it, because we're going to be debugging sound tomorrow as well. So I apologize for not getting some of those questions. We had to get to the no poop sauce logo. That was a pretty important question to answer. So ladies and gentlemen, thank you so much for joining me here on Handmade Hero. Obviously, if you want to continue the discussion, you can go to handmadehero.org. If you want a copy of the source code, you can always pre-order the game. It comes with a nightly build updates. You can go get the source code. In this case, it'll be an afternoon build update. I'll push the new source right now after we're done. And you can also email me a question. This will be turning, hopefully today, I'm really hoping, if I don't basically fall asleep because of this cold, I'm hoping to have the forums up and running too. This will email a question link, will turn into a link to the forums where you can ask questions and discuss things with the community. So watch for that, hopefully by tomorrow, if not later today. So hopefully that should be up soon. Thank you so much for joining us for another episode of Handmade Hero. 11 a.m. tomorrow again, so I hope to see you all here again tomorrow, including the folks from Europe who are able to join us. Thank you so much. Sorry we can't always be at a friendly time, but Fridays from now on will be Europe friendly as well. So thank you so much for joining us, and I will see you tomorrow.